This slide focuses on the penalty terms used to enforce constraints such as berth conflicts and crane assignment violations. Operationally, penalties must be large enough that constraint violations are never chosen just to reduce the objective. This slide introduces the idea of a problem Hamiltonian that encodes the quadratic, unconstrained binary optimization landscape. Operationally, this is the physics representation of the scheduling problem that the annealer attempts to minimize. This slide describes the annealing schedule, meaning how the system transitions from an initial easy state to the problem state over an anneal time. Operationally, annealing time and schedule affect solution quality and the probability of reaching the best configuration. This slide illustrates the quantum annealing architecture as a system for exploring quadratic, unconstrained binary optimization landscapes for large berth and crane instances. Operationally, treat this as a roadmap. It is not a replacement for all scheduling, but a potential acceleration approach for large integrated cases. This slide reports a scenario with 25 vessels, a 1,200-meter quay, and 20 cranes over 48 hours. The problem includes 15,000 binary variables and about 12,847 physical qubits after embedding. Annealing runs for 20 microseconds per sample with 10,000 samples, and reported end-to-end time is 0.2 seconds. Reported performance includes 94.7% of runs converging to the global optimum, solution quality of 99.2% of mathematical optimum, and average turnaround time 14.2 hours, which is an 18.9% improvement over classical heuristics. A classical solver times out above 72 hours for an exact solution. This practice question asks you to formulate a mixed integer model for 4 vessels on an 800-meter quay with 8 cranes. You use vessel length 200, 300, 250, and 180 meters with workloads 400, 800, 600, and 300 units. Arrival times are 800, 1000, 1200, and 1400. Crane productivity is 25 units per hour with 15% interference. This question asks you to implement a priority-based constructive heuristic for the same instance. You define a priority calculation, provide pseudocode, trace berth positions, start times, and crane assignments, compute the total objective, and discuss time complexity. This question asks you to design particle swarm optimization for 6 vessels and 12 cranes. You define particle representation, fitness, and constraint handling. You simulate 5 iterations with 30 particles and parameters. Inertia 0.7, cognitive 1.4, and social 1.4, then compare solution quality to the heuristic. This question asks you to develop a reinforcement learning formulation and consider stochastic vessel arrivals. It specifies a Poisson process arrival rate of 0.3 vessels per hour and asks how a deep queue network would be trained and how it adapts compared to static optimization. This question asks you to design a digital twin using AIS, Internet of Things sensors, and weather forecasting. For a terminal handling 150 vessels per week, you specify compute needs and performance metrics, then explain response to a disruption where 3 of 15 cranes break down. This question asks you to design a human and artificial intelligence partnership interface for 12 vessels with weather and customer priority conflicts. You include explanation mechanisms, feedback loops, and concrete examples of interventions and learning. This question asks you to formulate berth and crane allocation as a quadratic, unconstrained binary optimization for 5 vessels and 8 cranes. You define binary variables, construct penalty terms, explain quantum annealing, and estimate qubit requirements and embedding overhead. You provide speedup and solution quality expectations. To close, remember that berth and crane allocation must be solved together because timing, space, and crane productivity interact. Interference and contiguity constraints turn simple crane counts into realistic physical feasibility. Heuristics provide fast decisions. Particle swarm optimization improves solution quality with manageable computation, and reinforcement learning can learn policies that generalize across arrival patterns. Digital twins support rolling horizon re-optimization and disruption response. Quantum annealing offers a potential route to near real-time optimization for large integrated instances.